Hi guys, I guess it's math time. I wanted to show you guys some math. I did go to Harvard College, so I'm not sure what question is, can he still do math or can he do math? Anyway, I want to show you guys some math, if that's okay. First of all, um, there's such thing as complex numbers. Um, uh, a real number is a number that like we normally know, and that's the x-axis, and that would be real. X is real. And then the y-axis would be I times y. And the reason that's called, and I is the square root of -1. I equals square root of -1, which doesn't exist. That's why it's called imaginary. And so a number that's complex is the sum of a real number and an imaginary number. So z, a complex number, equals x plus I, y. So you can plot a complex number on this plane, not a line, but a plane. And any point is the x part of it, coordinate is the real part, and the y coordinate is the imaginary part. So if I have this point right here, it might be, this might be 2 plus 3i, because it go 2x, 3y on the y direction, so 2 plus 3i. So that's called the complex plane, or complex coordinate plane, if you want to call it that. Now I'm going to go into a formula that applies here. It's called Eulers Formula, and it is e to the I theta equals cosine theta plus I. Let me write it better. Make it so you can write it all in one line here. Okay, Euler's formula is e to the I theta equals cosine theta plus I sine theta. So e is a number that is the base of the natural logarithm. Its value is approximately 2.718281828, and it goes on like pi. It's similar to pi. It's an irrational transcendental number, constant. And e to the I theta equals cosine theta plus I sine theta. Cosine theta is the real part. That's the x part, x coordinate, right here. Y sine theta is the imaginary coordinate. So that would be like maybe here. And then the sum might be cosine theta plus I sine theta is an imaginary, a complex number, maybe right here on the plane. And complex plane, not, yeah. So, what do we want to do with this first? Let's see. I want to show an example, a special case of this, which leads to something called Eulers identity. Okay. And don't worry, I know this all seems like boring or whatever, but I had to do it. It's part of me. Math is part of me. So here's the complex plane again. That's x, I, y. So this is x, this is I, y. Now, let's say you have a circle of radius 1 on the complex plane. That means the radius, the distance from the center to the circle at any point is 1. And then I said I had, and theta is in radians, measured starting on the x-axis as 0 and going counterclockwise. And theta, and radians are such that a whole circular revolution is 2 pi, because there's 2 pi. 2 pi is the circumference of the circle if the radius is 1. So it gives you the measure, the length of the arc that measures out the angle. If the radius is 1, that measure of that, how much arc you've done, is the angle, is how big the angle is. So if your angle is 90 degrees, that would be pi over 2 radians, because if the whole circle is 2 pi, a quarter of a circle is pi over 2, because 2 pi over 4 is pi over 2. Okay, so let's see what we can do with this. Let's make theta 180 degrees, which is pi, because half of a revolution of the circle is half of 2 pi, and half of 2 pi is pi. So a 180 degree angle would be pi radians. Okay, and our formula was e to the I theta equals cosine theta plus I sine theta. So let's make theta pi. Okay, so make theta equals pi. That's right here, over here. Okay, the formula is e to the I theta. Well, theta is an angle, so I have e to the I pi here equals cosine pi. The cosine of pi is -1 because the cosine is the x value of it, and you're back over here at the negative side of the x, and you're at the circle. The radius of the circle is 1, so you are at -1. So cosine theta if theta is pi is -1, so we have cosine theta is -1, then plus I sine theta. Well, I is the y value, and it's 0 because if you're on the x-axis, the y component is 0. So you have plus 0 I, but 0 I is just 0. So what do I have now? Let's maybe erase the diagram so I can continue writing in the algebra part here. So I have e to the I pi equals -1 plus 0 equals -1. Okay, that's interesting. What about if I put the -1 on the other side of the equation of the equal sign? I would have e to the I pi plus 1 equals 0 because I just added +1 to both sides. That is a very interesting formula there. E to the I pi plus 1 equals 0. That's called Eulers identity. And that's very fascinating identity. I'm going to circle it here. It's fascinating because it's got E, which is one of the great transcendental numbers, transcendental irrational constants in nature and math. It's got I, which is the square root of -1, which is very important to complex variables, complex analysis, whatever we're doing here. Pi, which is the other transcendental irrational constant we have in math a lot. Pi is approximately equal to 3.1415927. Wait, 3.14159 wait, 3.14159 wait, 3.1415965. Yeah, 3.1415965 is how many digits I know it to, but it goes on and on forever. So it's got the three most important weird numbers in math, which is E, I, and pi. It's also got the additive additive identity 0, because when you add any 0 to anything, you get the same thing. That's an important number. It's got multiplicative identity because when you multiply any number by 1, you get the same number. It's got 1. So it's got 0, 1, E, I, and pi. Not only that, it has all three of the main operations in math. It's got plus, which is addition. It's got times because I pi is I times pi. And it's got exponentiation because e to the I pi is an exponentiation operation. So it's got e I pi 0, 1, addition, multiplication, and exponentiation all in one little formula. It's considered one of the most beautiful formulas in math. And people have asked, and maybe even asked themselves, what does it mean? And I don't know if anybody has an answer. I don't know if anybody can have an answer. I'm not even sure that question has an answer. That's an interesting question nonetheless. And I just wanted to do one more thing while I'm here with you guys. I know I better not make it too thin, right? I mean, that's enough for now. Enough math for today. And in engineering, which I studied at Harvard College, I concentrated on systems engineering, which uses Fourier transforms, sometimes Laplace transforms, but we focused on more Fourier transforms. But there's also Laplace transforms, which are very important in systems engineering for signal processing and systems analysis. And we always use LTI systems, which means linear time invariant, which means linear means if you get a certain amount of input, you get the same amount of output as you do if you put an input in, you get the same amount of output as if you put the same input in again. So in other words, it's linear, meaning if you put an input, the output doesn't change next time you put that same input. That would be nonlinear. But as long as you put the same input, you get the same output. That's linear. Time invariant means If it's time variant, means you can put something in the system and it gets one result now, but if you do the same thing an hour later, you get a different result. That's a time variant system. Well, we did time invariant systems, which means if you put a certain amount into the system now and do it an hour later, it's still the same amount you get. You still get the same amount if you put that same amount in. You still get the same amount out an hour later as you do right now. So we never got into nonlinear or time variant systems, but for practical purposes, linear time invariant systems seem to do good enough for analysis. Love you guys. Peace, rock and roll.